Wow, that was cool. Sorry, just eating Melkars. Glad you guys could witness the birth of a star with me. What was just born was a main sequence star, the starting star, that becomes all others, except, of course, a few oddballs. Main sequence stars are formed when huge clumps of gas, called nebulae, condense due to gravity into a ball of hot plasma called a star. This starting star, called a main sequence star, is the most prevalent in the universe, at about 90% of all stars that currently exist. Main sequence stars use something called nuclear fusion, which is fusing two or more atoms into another. These stars fuse the first element, hydrogen, into the second element, helium, through processes that release energy, which is why they're hot. Let's look at the anatomy to see the arduous journey energy must take to be released into the endless void of space. First, we have the core. Stars are big, at least these ones are, and because of this, gravity is pushing really hard on them, compressing the gas, making it hotter and denser. At the very center, you have the hottest and densest part, the core. The core is where all the fusion happens, where hydrogen is fused into helium, which releases energy. This energy gets radiated into the radiative zone, where it radiates as radiation. Energy travels as electromagnetic radiation, whom you may know as light. It actually takes quite a while for energy to get through this dense blob of sticky, gooey plasma. Some gamma rays can take up to 170,000 years to get through this mess in our sun, which is a main sequence star. After energy gets successfully radiated through the radiative zone, it must deal with the convective zone, a relatively cool current of moving plasma. The reason why this region moves is because of convection. It happens everywhere, from the sun to the wind to the center of the earth. When plasma is close to the core in the convection zone, it gets hotter from the radiating energy, becomes less dense, and rises. When it gets farther away, it releases the energy out into space, gets cooler, becomes denser, sinks, until it's closer to the core again, where it rises, then sinks, and repeats over and over again. This energy goes to the photosphere, the first layer of a star's atmosphere, and is the surface of it. This is where solar phenomena occur, which we'll get to later. Next is the chromosphere, the second layer of a main sequence star's atmosphere, which is full of a reddish hue because of the high amount of hydrogen that releases red light at high temperatures. Although hot to us, it is relatively cool compared to the corona, which is the last layer of the atmosphere. It is extremely hot and extends millions of kilometers into space. Solar flares and prominences may extend to this level. I should probably talk about them now, shouldn't I? Solar phenomena, which include solar spots, flares, prominences, wind, and coronal mass ejections, are all caused by the magnetic field, which I find very interesting. You see, electricity and magnetism are the same. It's called electromagnetism. Main sequence stars are made of a form of matter called plasma. It forms when gas gets so hot that their electrons fly off, ionizing them. Ionized particles are electrically charged, and when they move along in a star, it forms a magnetic field. The field influences the plasma's movement, which makes a magnetic field, which influences movement, which makes a field, which is a dynamic feedback loop, which is called a solar dynamo. When the plasma twists, loops, and folds back onto itself, the magnetic field gets twisted, forming loops on a star's surface. Sometimes plasma may hitch a ride on the loop, causing a solar prominence, which is a cool loop of plasma extending from the photosphere. These loops also store a lot of energy. When they tangle, snap, or reorganize themselves, they may release the energy in a sudden burst of plasma into space, which is dubbed a solar flare. The magnetic field may also limit heat from convection to reach the photosphere, which causes cooler and darker spots on the surface, which are called sunspots. A coronal mass ejection is a cloud of plasma energy and its own embedded magnetic field released into space, and is caused the same as solar flares, but just extremely powerful. The magnetic field can also carry plasma into space in the form of solar wind. Wow, that was a lot about main sequence stars, but how do you know if that star that I'm pointing at is a main sequence star or not? There are two main ways to identify main sequence stars. The first way is pretty simple. Main sequence stars are stable stars, meaning that gravity and radiation pressure, the energy they release, are in equilibrium, so they don't compress into infinite density, foreshadowing, or expand forever. They also have to fuse hydrogen into helium at their cores. The other way to identify them is to ask, is that star on the line in an HR diagram where luminosity decreases with surface temperature? What? Huh? What's an HR diagram? What do you mean by luminosity and surface temperature? Why is it on a line? Worry not. This section of the video is dedicated to answering those questions. So, first, what is an HR diagram? It stands for Hertzsprung-Russell diagram and is used to categorize stars. On the horizontal axis, we have surface temperature, which is the temperature of a star on their surface. Usually, the cooler temperatures on the diagram are farther from the origin, and the hotter temperatures are closer to the origin. Different temperatures have a different letter assigned to them. From hottest to coolest, the letters are O, B, A, F, G, K, N. Each letter has a color attached to them. It goes from a hot, vibrant blue to a cool, deep red. A way to remember the letters that traumatized me in science class would be, "Oh, be a fine girl, kiss me." A better way to remember would be, omniscient beings are firing giant knowledge missiles. On the vertical axis, we have luminosity, or absolute magnitude, or just brightness. Brightness is actually just the amount of energy a star emits. The greater the brightness, the higher on the diagram, while the less bright are closer to the origin. Main sequence stars are actually a spectrum on a line where the luminosity decreases with surface temperature. You may have bright and hot main sequence stars or dim and cool main sequence stars. Speaking of, red dwarfs are the coolest main sequence stars, formed as all others. They fuse hydrogen into helium in their cores, but more interestingly, they are fully convective with no radiative zone. Their core may even be convective. This is one of the many reasons why red dwarfs live for trillions of years, longer than all other main sequence stars. They make sure to use all of their hydrogen supply before dying, and are so small that they burn through it very slowly. Being so cool, temperature and complement-wise, they are a deep red and are the only main sequence stars that just fizzle out into white dwarfs, which we'll get to in the future. Surprisingly, their magnetic field is super strong, stronger than our sun's. They may even remain dormant for a long time before erupting super flares that may be 100 to 1,000 times stronger than the ones on our sun. They emit strong solar wind flares, prominences, CMEs, coronal mass ejections, and have sunspots. The core, convective zone, and atmosphere are about the same as our sun's, except a lot colder. Low luminosity, low surface temperature. Big main sequence stars, I have no idea what to call these, blue giants, are the hottest main sequence stars, formed as all others. These stars are so huge and strong that they are basically ripping themselves apart. They live for a short period of only a couple tens of millions of years, which is short on celestial timescales. They are magnetically active and hot. Really hot. They can be 15 to 90 solar masses and are the same as our average main sequence stars, just that they may be entirely radiative with no convection zone, except for the core might be convective. Wait, what? Why? Oh, apparently it's because they switch from proton to proton chain for nuclear fusion to the CNO cycle, which causes convective instability and such, which makes a hot convective core. Yes, they have magnetic fields. Yes, they have solar phenomena. Yes, they're blue. High luminosity, high surface temperature. Yay, that was main sequence stars, but we forgot about something. The predecessor of a main sequence star. The real first star, or a clump of hot gas, depending on how you classify them. A protostar! Protostars are the stage of a star when gas in a nebula has started clumping up but haven't yet started nuclear fusion. You have this hot sphere at the center of a huge accretion disk flattened by angular momentum. There's a magnetic field from a solar dynamo, solar wind, and jets of plasma, which shoot out of the protostar's poles. This is the first time we see this, but this will occur more in later evolutions. Jets from protostars are caused when charged plasma from the accretion disk gets ejected outward by the magnetic field. It is thought that these jets are crucial because they decrease angular momentum, which allows protostars to accrete properly. Some gas from the protoplanetary disk may even become planets. There are a few areas that mark which substances may condense into planets, starting with the central region, where only metals and minerals may condense into planets. Outside of the soot line, carbon compounds may be part of planets, and outside of the frost line, volatile substances which can evaporate in low temperatures, such as water, ammonia, and methane, may become planets. Most materials in the accretion disk is hydrogen and helium, which don't condense. The core of a protostar is not hot or dense enough to support nuclear fusion. After accreting enough material, however, it may become a main sequence star and live the rest of its happy life. But if it doesn't devour enough gas, it is a failed star. brown dwarf. If a protostar doesn't consume enough material and is less than 0.08 solar masses, it will be a brown dwarf. Brown dwarfs technically fuse hydrogen into helium, but it's deuterium, heavier hydrogen, fusion, which requires much less energy to support. These clumps of gas are entirely convective. Yes, sometimes the core, and no, not because it switched fusion methods. They are about 3 to 80 times bigger than Jupiter and are so cold that they have weather. With an atmosphere of hydrogen, carbon monoxide, methane, and ammonia, there are clouds of metals and silicates that occasionally rain iron out of the sky. They have a magnetic field and may sometimes have X-ray solar flares. Since these are so small, they fuse very slowly and live very long lives. Enough talk about these failed stars. Let's check on the main sequence stars again. Oh, why do we have a red giant? Oh, yeah, how could I forget? When a main sequence star has accumulated enough helium in their core, gravity pushes on the star and ignites the helium, starting helium burning. There's a core of burning helium, which is so hot that a shell around the core starts burning hydrogen. Around that, a thin layer of radiative zone and a convective region of hydrogen that makes up the rest of the star. All of the energy from the combined fusion of hydrogen and helium pushes against gravity, expanding the star. The star is a giant and looks red because although hotter at the core, it is so much more inflated that at the surface, it is cooler because the heat is spread over a much larger surface area. If you have a low-mass star like our Sun, it may stop here with a core of carbon and oxygen that may become a white dwarf. But if you have a larger star, then it must keep going. When there is enough carbon in the core, it ignites, giving us a core fusing carbon, a helium-burning shell, a hydrogen-burning shell, a thin radiative zone, and a convective region. The star is bigger, cooler, and redder. When there's enough neon in the core, it ignites with the burning shells, the radiative and convective zones. Then there's oxygen in the core, followed by silicon, which fuses into iron. Each time the star becomes bigger, cooler, and redder. They are K or M on an HR diagram with a luminosity of about 3,000 suns. These may have a magnetic field in the solar phenomena, but most red giants don't or have weak solar activity because the bigger an object is, the slower it spins, a property of the conservation of angular momentum. This slowdown spin weakens or limits the magnetic field, which also limits all solar phenomena. Red giants become beasts when they have a core of iron, or even a core of carbon and oxygen. When a red giant of a small or average main sequence star has a core of their valued carbon and oxygen, they become unstable, start pulsating, and the power from the core causes the red giants to shed their outer layers, leaving a beautiful planetary nebula in their dead core, called a white dwarf. White dwarfs are dense, really dense. From when gravity was pushing on them from all angles, they compressed. The core became really dense, and it shows in white dwarfs. White dwarfs are about the size of Earth, but can be half the mass of the Sun. Half of the Sun fit in a sphere the size of Earth. They are 200,000 times denser than our planet. This star is only held together by something called electron degeneracy pressure, the property of quantum mechanics that states that no two electrons can occupy the same space. In other words, electrons repel each other. Although dense, there is no nuclear fusion in the white dwarf because carbon and oxygen are really hard to fuse. White dwarfs are pretty simple anatomy-wise, for they only have a core of carbon and oxygen, which is the vast majority of the star, a thin layer of dormant helium, and a thinner layer of dormant hydrogen. They have an atmosphere of hydrogen and helium that very slowly radiates heat into the universe. That is the only way white dwarfs release heat because their immense gravity doesn't allow them to have solar wind. And because this process is very slow, white dwarfs live for very long periods of time. White dwarfs and red dwarfs may be the last stars in the universe because they both live so long that it's basically forever. Although completely radiative at first, as it starts to cool, there's some convection going on in this white husk. At first, it is pretty rare for white dwarfs to have a magnetic field, but as the carbon and oxygen start crystallizing as a white dwarf gets cooler, magnetic fields are much more prevalent. The gravity also doesn't allow any solar phenomena, even if the white dwarf has a magnetic field. They are in the bottom left of an HR diagram because they are very hot but not as bright. And yes, white dwarfs are white. As a white dwarf keeps cooling, it becomes less of a star and more of a rock. Once all the heat is radiated away, it becomes a black dwarf. Black dwarfs exist. Or do they? Black dwarfs form when a white dwarf eventually cools because white dwarfs make no new heat. However, it will take so long that no black dwarfs exist yet, so these are all predictions smart people think will be true. When white dwarfs start to cool, the carbon and oxygen crystallize under the immense pressure, making diamonds. Black dwarfs have the same anatomy, but everything is much colder. They are still very dense and that's it. They used to be a star, but now they're a rock. There is nothing else interesting I could find about these. No, they don't have a magnetic field. Yes, they're black. No, they're not actually stars, so they're not on an HR diagram. Now, what if your main sequence star was huge and became a giant? If it was, it may be a blue supergiant. Blue supergiants are so hot and powerful that although they become big, they still glow blue. They usually become a red supergiant after fusing more elements in their core, but these giants are just built different. They act just like red giants, just much hotter and a bit smaller. If you have a blue or red supergiant with an iron core, what happens next? You'd think that they would fuse it, but iron takes more energy to fuse than it releases. With no radiation pressure to combat gravity, gravity wins and keeps compressing and compressing. It gets so bad that at the core, the electrons get so close to the protons that they fuse into neutrons. This collapse blasts everything away, causing a type 2 supernova, and leaves the dense neutron core as a neutron star. Neutron stars are some of the most intense things in the universe. First of all, they are dense, really dense, more dense than a white dwarf. If a neutron star was the mass of the sun, instead of being the size of Earth, it would be 10 to 12 kilometers wide. That's the sun in a small city. They're the second most dense thing in the universe, right behind black holes, but they're hacking anyway, right? Zero volume, infinite density, you've got to be kidding me. Other than being super dense, they also have jets spewing out of them. Remember them? Protostars had jets because of their magnetic field, but you need charged particles for that. Neutrons don't have any charge, and this is a neutron star. Well, neutron stars aren't entirely neutrons. There are still a little bit of protons and electrons in the star, and since they are so hot and flowy at the core, they generate an incredibly strong magnetic field. This field funnels protons and electrons into these huge jets, for neutron stars rotate incredibly quickly. They rotate hundreds of times a second, and the fastest known rotating neutron star makes 716 rotations around its axis each second. This is because when an object gets smaller, it rotates quicker, another property of the conservation of angular momentum, and these stars are really small. Usually, the magnetic poles are misaligned from the rotational poles, so when the star rotates, jets sweep across every direction. Sometimes, a neutron star with a magnetic field 1,000 times more powerful than a regular neutron stars may be born. They're called magnetars and rotate slowly in comparison to regular neutron stars. Completing a rotation once every 1 to 10 seconds, it is theorized that magnetars are formed when a star has an extremely magnetic core by merging with another star, which becomes a neutron star. Anyway, neutron stars are built like planets, with a crust and a molten core. Not because they're cold like planets, neutron stars are incredibly hot at their surface, but because of the pressure gravity brings. The densities are so high that it solidifies a cooler surface. The crust starts off as iron nuclei with mostly neutrons, but with some protons present. There are electrons flying everywhere, and as you get deeper, the nuclei get more and more neutron-rich, until they are almost entirely neutrons. The deeper we go, the stronger the crust gets. This material is called nuclear pasta, one of the strongest things in the universe. It has a couple phases, starting with the Inoki phase, where the nuclei form into many little spheres. As there is more pressure deeper in the crust, the sphere compresses into long rods called the spaghetti phase, which under even more pressure fuse into sheets called the lasagna phase. These can keep compressing into more bizarre shapes, but you get the point. As you go deeper, there's more pressure and it gets significantly hotter. You eventually get through the crust and reach the outer core full of free neutrons, protons, and electrons flying everywhere in this soup. As you go even deeper, you reach the inner core, and this is where we're stumped. We have no idea what's in the inner core because the heat and density is so great. It could be a quark gluon plasma, where the neutrons and protons go back to being quarks, what they're made of, like they were immediately after the Big Bang. Some of those quarks may become strange matter, an unusually stable kind of matter. They may also just stay neutrons and protons, but we don't know. The atmosphere of a neutron star is 4 inches thick, 2 million Kelvin, and as dense as a diamond. It is made of hydrogen, helium, and carbon. The gravity on a neutron star is 100 billion times stronger than that of Earth's, and the only way a neutron star can have an equilibrium against gravity is something called neutron degeneracy pressure. Like electron degeneracy pressure, neutron degeneracy pressure is the neutrons not wanting to occupy the same space and repel each other. But what would happen if neutron degeneracy pressure loses against gravity? Would another force fight against it, or would it just keep compressing? What would happen if you just keep squeezing? If a neutron star is too massive, neutron degeneracy pressure isn't enough against the behemoth of gravity, and it squeezes on the neutron star with no stop. Gravity won and won't be stopped. What you get as a result would be a black hole, which doesn't seem like a star, but is a black dwarf one either? Black holes are weird because their gravity is so strong that light can't even escape. So, although black holes may seem big, technically and mathematically, they are infinitely small. They seem big because of their black border, the event horizon. The event horizon is a point where light can't escape because of the immense gravity and occurs at the Schwarzschild radius. The more massive a black hole is, the larger the Schwarzschild radius and the bigger it appears. Another scary thing about black holes is that since light can't escape, nothing can. If you fall in, you're not getting out. Nor is anything else. Black holes eat a lot and usually have an accretion disk of hot plasma around it. Something fun about this is that the black hole bends light, so you could see part of the back of the accretion disk as humps above the black hole. Black holes don't inherently have magnetic fields, but their accretion disk causes a solar dynamo, which does give a field with no solar phenomena because nothing will escape. This magnetic field funnels material from the accretion disk into space, creating beautiful jets. This magnetic field and other factors cause the corona, one of the most hostile places in the universe. At billions of degrees, full of hot plasma and X-rays, I certainly would not recommend. Other than the event horizon, which I already explained, there's an event horizon shadow, which is about 2 times larger than the event horizon, is completely black, and is caused by the distortion of light near the event horizon. In the event horizon shadow, you may see a ring of light from all angles called the photon sphere. It is caused when light literally orbits the black hole. I should probably explain what's causing this high gravity, shouldn't I? Well, at the center of the black hole is the singularity, which is a hypothetical point of infinite density and zero volume, which sounds impossible, and it is. Or at least we think so. All of that matter compressed into an infinite dot in space. Anyway, black holes don't obey the laws of physics, and scientists are losing their minds about it. Is the singularity a place in space or time? Or black holes windows to different universes? Help, please, my entire research team is going crazy. Wow, black holes are interesting. And there are so many things that I didn't cover about black holes that I could make an entire video about them. Wink, wink. We did it! We covered every relevant star and the entire history of a star's life. From main sequence stars to black holes, with many stars in between. From protostars to main sequence stars to giants to remnants. From cores, convection, dynamos, jets, solar phenomena, fusion, radiation pressure, gravity, supernovae, degeneracy pressure, and infinite density. I've just been wondering one thing. What actually is a star? Is it a spherical object that supports nuclear fusion? No, then a white dwarf or neutron star wouldn't be one. A fixed point in the sky? No. What? No way! Is Venus a star? I can't believe Oxford Languages says that. Even Wiktionary says that a star is a ball of plasma that goes through nuclear fusion. My favorite definition that I, myself, have made would be that a star is a spherical object made of plasma in space. It covers white dwarfs and neutron stars, and let's face it, black dwarfs are never stars. black holes because we don't know what's in the center. Well, thanks for watching me ramble about stars for 4,500 words. I hope you learned something. We really need a better way to classify what is and what's not a star, and have fun watching our star go through these stages.